Hey everybody, welcome to the new semester, and we have SpongeBob there also here to welcome us back to the new semester. So for this CS 302 assignment 1, we're going to implement our own custom linked list class. Now, you're not going to have to worry about implementing your own custom main file, just a linked list class implementation, and I will provide you with a set of main files you can use to link to your linked list implementation file to test out test all the features out for your linked list class. Now, it will be important to make sure your linked list class works correctly because you will have an assignment later in the semester where you're going to have to use your custom linked list from this assignment to implement a set of sorting algorithms. So let's first go ahead and discuss the header file provided and just go over the overview of the linked list class and all of its nested classes. And then I'm going to use OneNote to draw out the structure so you can help you visualize how we're going to implement this custom linked list class. Okay, so in the PDF, we have our linked list class defined right here. So you can look that over. I also did provide you with some explanation for different members of the linked list class. Of course, you can read this on your own. And of course, in this video, I could read this to you. But again, I think that'd be kind of a waste of time if I would just read this to you right here. So I'm going to actually just explain this in my own words right here. I have the text editor set up. So I'm going to go ahead and just, in my own words, explain this. But again, you can read through this if you would like. So anyway, here's a linked list class right here. So we have first our header guards, which of course the header guards are important. So if in case you redefine the linked list class somehow, this will block you from redefining it, from causing any compiling errors. So always important to have these header guards at the very top. And right there, it closes the header guards up. So our linked list class is going to be a two-directional circular linked list. So I like having it circular and two-directional because it makes it more versatile and more flexible. So now again, in the C++, in the STL list class, I believe in Linux, it does have it work as a circular linked list, but I think that's undefined behavior. But we're going to have it be very defined behavior. We're going to definitely have our linked list be circular, and it won't be undefined. It will be very well implemented this way. So also the linked list class will be a template class because, well, as you recall from CS 202, a linked list is just a container class. So it makes sense that really a linked list can store a list of anything, integers, strings, or custom types. So really making it as a template is, I guess, that makes the most sense. So let's go ahead now discuss our class. So we first have our private members up top, and we first defined a class node within our linked list class. So remember, the node is going to just be essentially each block in a linked list is going to be a node, if you recall from CS2. So I made this class not a struct node because, well, a class is fancy. And again, from SpongeBob, you remember Patrick, when he was talking about, being fancy to SpongeBob, he said, have your pinky out always. This is kind of our version of pinky out, but we have everything as a public member. So really, this is just going to be a glorified struct, but it's more fancy having a class instead. So class node, everything's public. So it's really just a struct in disguise. So now we look at our class. We have our data field and we have our pointers to our left and to our previous node and our next node. So this is going to implement this doubly linked or this two-directional structure. We have these constructors right there, which again, you don't have to use them, but it does help initialize our node correctly so we can set, the data field or set a default. And of course, we can initialize our pointers to be null like that. So again, you don't need to use these, but it can make it a little easier when you have to insert new nodes. This constructor kind of makes life a little easier. So that's going to be our node, very similar to the one from CS202. And then we have this other private member in our linked list class called node star dummy. You may wonder, well, if it's a two-directional linked list, where's the head and tail pointer? Well, this node is going to allow us to access both the head and tail. So it's going to be a nice structure. So when I draw the example out on one node, I will, show you how this will look, and hopefully then it will make more sense. But anyway, that's going to be our tail and head pointer essentially. Now we have our class iterator defined in our public label in our linked list class. And again, the purpose of making this public is because we're going to actually allocate iterator objects outside of our linked list class scope. So it makes sense to make this class a public member, not private like we did for node. So iterator class is going to just be really a fancy pointer. So more fancy talk, I guess, going on here. But iterators are used actually in STL. So when we have STL list, STL vector, and so forth, they use iterators as a way to traverse through your structure. So the whole purpose of an iterator is that you can navigate a linked list like if you had a pointer, but you kind of keep the pointer data hidden is the idea. So in our iterator class, we have our node star current, which is going to simply store the address of a node that the iterator points to. So that's going to allow the iterator to point to a node in our linked list. And then here's our public members. Now, I have everything implemented for you in this iterator class. Don't worry about implementing iterator. It's already there for you. You have to simply use it, essentially. Now, you might not have to use it too much in this assignment, but in the provided main files, it will use iterator in those main files. But the iterator is implemented for you, so don't worry about implementing this. It's given to you. This friend class is important right there because if you don't have this, we're not going to be able to access the private member of iterator object within the linked list class scope. So this is important to have that. And then we have essentially our constructors that initialize our current fields. This is going to be our dereference operator, if you will. It's going to return the iterator objects. So the iterator points to a node. This operator returns the node's data field. So this is going to almost work almost like dereferencing a pointer. Similar kind of logic there. Now we have our two operators, our postfix and prefix plus plus operators. Essentially what those will do is it will move the iterator over to the right in our linked list. That's all it does. And we'll see some examples as to how it does that. Then we have our minus minus operator functions, which is our pre and post order, pre and postfix operators. And these operators will just allow the iterator to move to the left node in our linked list. And we'll see some examples of that later on. Then we have our comparison operators there. Just going to compare if two iterators point to the same node or not. So that's essentially what the iterator class does. It's already given to you, so you can just simply use it in your program as needed. So now we have our linked list class. So we have our constructor, which will initialize our linked list. It will set our dummy node up correctly. Our deep copy constructor, our assign operator, and destructor, fairly similar to CS202's constructors. And assign operator and so forth. Push back and push front. So push back will do a tail insert. Push front does a head insert. And I'll show some examples of that in picture later on. Pop front, pop back. So pop front will remove the front node, a head removal, and pop back will be our tail removal. Is empty function is given to you. It returns true if the linked list is empty and false if it's not empty. If a linked list only has one node, just dummy, then it's essentially empty because we don't have anything relevant in our linked list. The front and back function is given to you already. The front returns the front node's data field, and then the back returns the tail node's data field. So nothing fancy there. The remove node function is going to pass an iterator into this function. It removes the node. So essentially pass iterator in. Iterator points to some node in your linked list. The remove function removes the node in which iterator points to. That's what this does. The begin function returns the head node. The end function returns the dummy node. And then swap function will swap two nodes in your linked list. Now this function will be rather challenging because we're not going to simply just swap data fields of two nodes. We're going to physically move these two nodes in the linked list, it's actually more efficient to do it that way, but it is a bit more complicated. So I would imagine that the remove node might be a little bit tricky and swap will be a little bit tricky. So now I'm going to go ahead and just using OneNote, I'm going to go ahead and draw some pictures to help you visualize how these push pop functions work and how the iterators kind of work together with our linked list class. Okay, so here's a snapshot of our linked list object. So I used integer type, not string, for this example because I'd rather just use integers since they're simple to come up with on the fly. So when you have your constructor for your list class, what you're going to do is you want to just set the dummy pointer to point to a new node. So you would allocate a new node and assign dummy pointer to this new node. And then all you'd have to do is just set dummy arrow previous equals dummy and dummy arrow next equals dummy. So that way this node's next and previous both refer to itself, and this really denotes an empty linked list because there's no relevant nodes in our linked list. Now, in this example, consider, let's say we did a bunch of insertions in our linked list. Let's say we did a pushback 7, pushback 3, pushback 2, pushback 4. This is going to be your linked list at that point. So you can see here that your head node is right there. So look at it, dummy arrow next. So this is going to be the next field of the dummy node. It points to the head node. So dummy arrow next points to the head, which is that node right there that contains 7. Now consider dummy arrow previous, which is this field right there. That pointer points all the way to the end of the linked list right there. That's going to be your tail node. So you can see here, dummy arrow next will be used to retrieve that head node, and dummy arrow previous retrieves your tail node. So now the question is, how do we do a push front in this linked list? So to do this, let's suppose for right now, let's just say we did something like list dot push front, let's say 5. So I want to push 5 in front of our linked list. So the way we would do this is, first of all, in our push front function scope, we first have to allocate a node. So let's say for right now I create a node. I'm just going to call this just temp for right now. And I just put this actually over here to the right. So we have temp. And let's suppose we allocate a node to temp. This part shouldn't be anything too complicated. So very simple, allocate a new node like that. And I'm going to store 5 in here. So how do we do that? Well, under temp arrow data equals that parameter. So that parameter contains the value 5, and we store it in temp arrow data. So we store 5 into that node. Easy peasy. So now we have to simply insert this node between dummy and 7. That's going to be our head node insertion. So, I mean, one easy way to do this is what I would do is I would maybe just create a pointer. Maybe just call it head pointer I would create a local variable. So create a variable locally inside the push front function body and set it equal to dummy arrow next to help you out. So that way you have a tail pointer, or not tail, sorry, head. You have a head pointer that points to that node right there. It makes things a little bit easier. So now what we have to do is set dummy arrow next to point to temp. Well, how do we do that? I mean, same as in CS202. So dummy arrow next equals temp. So it's going to set, oops, too much I deleted right there. Oh, never mind, this is actually fine. So anyway, so what will happen is you want to set dummy next to point to this new node. Like that. And you want temp previous to point to dummy, because you have to link these up. So the idea is you want to insert this new node between dummy and head. And then what we have to do is set the head pointers previous to point back to this node. And then this node temp next equals head. And now you can see here, it's a very ugly picture, but we can see here, is the result is that this node 5 has been inserted between dummy and head. So essentially, every single update, every time I drew a new line, that's like one single C++ statement. So I set temp equal to new node, node start head equals dummy next. When I said dummy arrow next equals temp, that was one statement. Temp arrow previous equals dummy, and so forth. But the idea is that we have to allocate a new node and insert it between dummy and this head node by simply setting, these two nodes have to be wired up to each other. And then these two nodes right there also have to be wired up to each other. That's the idea. Now, this doesn't consider the edge case where if you have an empty linked list, there's going to be an edge case to consider. This was the case where if the list was not empty. So if it's an empty linked list and you do a push front, make sure you handle an edge case. Now the edge case is really this. If you do a push front, then this node will be simultaneously the head and at the same time the tail node. So make sure you're consistent. Because remember, in this case right here, the tail node's previous has to point back to dummy. So for a case like this, let's just consider the following. So let's say if I insert into this linked list right here. Well, what would happen? We allocate a new node. Let's call it temp for now. We have to make sure that dummy next points to it. This node points back to dummy. And then dummy previous has to point back to this. And his temporary nodes next has to point back to dummy. So make sure you handle that case as well. So I'm going to cover the push front. I'm not going to cover the push back, but push back is fairly similar. So same idea, you have to insert something between dummy and this tail node right there. So I'm not going to cover push back. I'll let you kind of figure it out, but the idea is you want to insert something between dummy arrow previous and a node after. So let me just sort of draw this up really quickly here. So I'm going to erase this really quick. So for pushback would be like this. So suppose I redrew my linked list a little bit, or I put dummy right here instead. I'm going to reposition dummy. So we have this scenario right here. Like that. So for pushback, we have to insert something between these two nodes. So if we look at it, you can essentially, you could set a tail pointer in the following way. You could say node star tail equals dummy arrow previous. And have a tail node that would be assigned right there. And then of course you can just allocate a new node and insert it between tail and dummy by correctly linking up these previous and next pointers accordingly. So that's the push back and push front function. So let's go ahead and now talk about the iterator class just a little bit. So I'm going to refer to this original linked list from before. So let's go ahead and just talk about how would I be able to iterate through this linked list. Well, what we can do is similarly given to you in those provided main files, but I want to just simply draw it out here to help you out. So we would have to define an iterator using either the auto keyword, or we can just use the following convention. So iterator is a class type defined within the linked list class. So we have to put the scope operator right there, because otherwise we won't be able to define iterator type in main. So we use this approach. So we have this iterator object, which I'll put here in green, and we'll put a box here for it. So it'll look like this. So we have an object, and just going to contain some space for it. And within the object iterator, or IT, we have this current field, which is going to be a pointer within this object. So right now it points nowhere. But what we can do is we can say IT equals list dot begin. And the begin function, returns an iterator whose current equals head. And we're going to assign this iterator object into IT. So long story short, IT is going to point to that node right there. And then, of course, if I were to do something like IT++, it's going to move the current over to the next node. And I could, of course, can say something like cout star IT, which will output 3 because it's going to reference the current pointer, access that data field of that node that IT's current points to, and returns it. So it's going to return 3. And again, we could, do IT minus minus even, which moves it to the left, moves it back to the previous node. So very simple, easy to use iterator class. So that's all there is to it. Now, again, if let's say we do IT minus minus again, it's going to hit the dummy node. And if I do IT minus minus again, it will wrap around back to the end like that. So we can, of course, write a loop where we can start from begin and then do IT++, and while IT does not equal to the end, it will just keep on iterating through each node. Once IT does equal the end iterator, so we can do something like this. So again, if we do something like IT equals list dot begin, and then while IT is not equal to list dot end, we can just maybe do IT++. So essentially, start from the beginning, we increment IT by 1, and once it hits the end, so it starts off at the beginning, it jumps here, then jumps here, jumps to 4, then it will go to the end iterator, the end function returns the dummy node. So once it hits dummy, it fell off the linked list, essentially. So very easy way to traverse it. Now, of course, you can traverse it from right to left as well, but you have to set the iterator not to the end, but to the minus minus end. So you have to do something like this then. You have to do while, you have to do first IT equals list dot end. You must do the minus minus though, because the end returns the dummy node, not the tail node, but then minus minus in front of the end returns the node right before dummy, which would be our tail node. Then of course, while IT is not equal to list dot end IT minus minus. And if you do that, what's going to happen is it starts off at the very end, minus minus, and moves it this direction. When it hits the front node, minus minus again, it will go back to the dummy node, which means it fell off the linked list bounds, which means that it hit the end. So we can see here it's a very nice way to set this linked list up. So that's kind of how the iterator class can be used. And of course, you can refer to the sample main provided. And also you can look at some sample code for the STL list class as well, which you can kind of get an idea of how iterators work as well. But it's just really a simple, just a way to traverse the linked list, basically. That's all there is to it. So now let's go ahead and talk about these last two functions that involve using a linked list. So we're going to go over how to remove nodes using iterator. And then, of course, we will discuss the swap nodes or swapping function in our linked list class. Okay, so let's say you want to look at the function to remove a node at a position that the iterator points to. So let's suppose you want to remove 2 from the linked list. So we have our iterator set up where it already points to the front node. So if I were to do, let's say, IT++, I did IT++ again. Then it moves the iterator over 2 spaces or 2 nodes over. So an IT would point to this node right here is the result. Now, if I went ahead and said something like list dot, I think it's called remove node, and I passed in IT. We want to remove the node that IT points to. So this node is going to be deallocated at the very end of the day. But remember, how do we remove nodes in a linked list? Well, we have to essentially, within the function body, we have to have these 2 pointers that point to our surrounding node. So we have to make sure that we first have that set up. So again, within the remove node function, we can define or we can declare multiple iterators or even node pointers. Up to you how you want to do this. I think within the linked list class, it might be easier just to use pointers because you can access pointers directly within the class, no problem. Iterators are mostly used in main to allow us to, navigate the linked list freely without pointers. So within the linked list class, I would just suggest create some node pointers. So we have these 2 pointers surround too. And remember how this works. You need to make sure you set this pointer to point here, set that pointer to point there. So now 2 is unreachable. And then you just have to then deallocate this node and then make sure you set the current afterwards to point to the node after we just deleted. Which wouldn't be hard because if you do have the address of this node right here, then you can simply assign that to that iterator's current field. That's the result. And again, you have to also make sure you check for edge cases. So if the current if IT current points to the head node, then you want to make sure you have a special case fit. Now again, if you wrote pop front and pop back, you can just use those right here in this remove node function. So again, make sure you check if IT points to the head or to the tail node. Maybe have a separate logic for that. And of course, this is right here. This example I showed you was more the general case where if IT points to some random node in the linked list. So there we are. Now let's go ahead and cover the more difficult function, which I have a lot of test cases I have in CodeGrade for this, which is going to be the swapping function. Let's get into that last. Then I'll go over just, I'll show you the, then I'll show, of course, the sample mains and go over compiling and so forth. But let's discuss swap next. Okay, so I have this linked list drawn up here, so there's no dummy node. So suppose you have a giant linked list, but we're going to kind of hyper focus just on this part of our linked list. So suppose you have I and j iterators, and we have them in this position like this. So you want to swap I and j. You want to swap 1 and 5. Now, of course, it'd be simple if you could just simply swap the data fields like that. That'd be so easy, right? But we want to make use of a linked list because let's suppose you have a big amount of data in each node. So you have a vector in each node or something. Then it could be an overhead to copy data fields. So you want to be more efficient and just simply pick up these 2 nodes. And the idea is you want to essentially do this. You want to take this node, pick it up, pick this node up, drop it there, and drop this one right there. That's what we're trying to actually do. That's kind of the action we're trying to do actually. So let's see, how do we actually code this? Well, I guess one way to think about this is, I think I went back too far. So really each node is here by context. So the idea is, well, this node exists because 3 points to it and 7 points back to it, right? And this 5 node exists here in this position because a 2 node points to it and 8 node points back to it. So that's sort of the key to this. So what you want to do is the following. So this is one of the cases where when I and j are not adjacent to each other. So here's what we have to do. So you want to make sure that the node to the left of I, which is, I'll put this pointer right here. In order for j, so 5, to come after 3, we have to make sure that 3 points to this node. So we have to just set that node's next to point to j current. So I would suggest in this function swap, allocate several pointers. So I would allocate, 2 pointers, one that points to the left of I, one that points to the right of I, and likewise one that points to the left of j, one that points to the right of j. I mean, I would say it's a good idea. I would just do this to help me. So create additional pointers like this. So that's your first step. And then j has to point back to 3. So j current previous points to this node right there. And of course, we're not done yet because now we need to make sure that this j current, its next, points to the node after I. And this node has to point back to j. So, and then we're still not done yet, because now we have to make sure that it has to point to the node that J was pointing to. So I has to point over there. This node points back to I. And we're still not done because I has to point back to this node. Oops, actually I shouldn't have erased that. And then this has to point to I. Ooh. And if you were to simply like pull on the ends of this linked list, the I and J would actually physically would move with it. So this is almost reminds me of in SpongeBob where we're not talking about this or this, we're talking about this. And he draws all these lines on the screen. If you watch the episode where Mr. Krabs is trying to win the affection of Mrs. Puff. And you know, this reminds me of that exactly. So that's how you would do this. You have to do a lot of rewiring because you have to make sure that at the end of the day, 3 points to 5. So let me just see if I can go back to the very, very original. But this is kind of how the code would look like. So you can imagine how much of a nightmare fuel this is going to be. Okay, let's put it back to where it was originally. So the idea is we have these nodes right here, 3 and 7. So 3 has to point to 5, 5 points back to 3. 7 points back to 5, 5 points to 7. And if you do that, then 5 is relatively after 3 and before 7, so 5 is going to be in this position from now on. And the same idea, if let's say we want to put 1 over here, then 2 has to point to 1, 1 points back to 2. And then 1 has to go to 8, 8 has to point back to 1. And if you complete that, then yes, you complete the process. So now what's going to happen, the end result will be this. So this 1 would move, but then also I moves with it to make things even worse. The pointers really are, shall we say, fun in C++. We love pointers. They're great. So the end result will be this. Now the problem is this though. We want to have it where so in this case here, we want I to still point in this position. So let's suppose this happened to be the second node in the linked list. Let's just say for right now. We want I to still point to the second node of the linked list. So we have to set I's current, assign it to this node. We have to set J current to assign to this node. We have to reassign I's current and J's current because the result is you want to have it where I still points to the same respective position of our linked list, and same thing for J is the idea. That was one case right there where I handled it where when I and J were not adjacent. You have to also handle a case, what if I and J are adjacent to each other? You also want to handle a case, if I and J are the same, then don't do anything. You can actually assume that I will always be to the left of J. So you can always make that assumption to make things easier. But what if I happens to point to the head node? What if I happens to equal dummy arrow next? What if J happens to equal dummy arrow previous? What if I and J are both? What if I is the head and J is the tail? So there are a couple of edge cases to consider. But that's the idea of swap nodes. So again, I would suggest draw this out on paper or on your iPad or wherever and go through the steps step by step. But just remember, when we swap two nodes, they're all relative to each other. So make sure that the neighbors of I and neighbors of J point to the new node. And of course, when you do that, essentially the two nodes move their position in the linked list. So I'll leave that part so I kind of went over just one example, but you want to draw this out to make sense of all this. So now let's go ahead and just go over compiling the code and just working with it, just so we can get an idea of how to compile and run everything for testing purposes. So here's a header file that's given to you, and of course here's an implementation file that is a skeleton code. You have to fill in these function bodies, basically, is the idea. Now this right here is needed because if you want to be able to externally link our header to implementation to the main, we have to have these explicit template definitions right there. Now, the purpose of this is because for assignment 1, I don't want people to be able to update the header file. So by doing this, you're not able to submit your own custom header file. You have to submit just implementation file. But a header file like this will be actually available in CodeGrade. It will link that to your implementation file. So if you try to modify the header file, then it will not compile on CodeGrade. So you're going to be forced to have to write the functions as instructed. So you can't, let's say, for example, you don't want to handle dummy pointers and circular linked lists. Well, you can't change it because if you try to change it, it will not compile on CodeGrade. So that's the purpose of this. So we want to have separate file implementations. So that's why having these in here will allow us to link these externally. So that way you won't be able to mess with that. So now what about how do we compile? So for example, let's look at, let's see, which one should I look at first? Push test. Okay, so here we go. Here's an example that is one of the mains you're going to be using to test out your class. So to compile, same as in CS202, G++, we have ll.cpp, and then we're going to have this ll push test.cpp. So essentially, you have your header file included in both files, in this file and in your implementation file. So then that way it will kind of include these definition of linked lists in both files. And then to compile, we just do that. We have a.out, we run a.out, and there's the output. If you wanted to say you want to test out the, let's see what other files you want to work with here. So if you want to test out the pop test, well, same idea. We just do G++, llcpp, and we're going to do ll pop test. So just like in 202, this will be your class implementation file. That's going to be your main file. It will link these two and create one a.out. And this is sort of the results of the pop test. So you can, of course, test out all of these. You can test all of these out, basically. So I gave you several of these. This will test out most of your class. And I have it where a lot of these outputs also output the list from left to right and right to left to make sure there's no broken links as you are inserting contents into your as you're testing out these functions out. So basically, for submission, you have to only just submit your ll.cpp file. All these mains will be given to you. You can, of course, just link them to your custom ll.cpp file. I'll also give you the header file as well. But for submission, only submit your implementation file to CodeGrade, and it will link that to the header file and to all these main files that are provided. It will link them all, and it will run each of these individually, and it's going to basically it will test out all the functions out in your linked list class. So again, now if you want to actually, we also would check on CodeGrade for memory leak check. To do that, once you have your program compiled, so let's say I'll recompile my code, you can, of course, run valgrind.a.out. And valgrind is a command in Linux which will check your program for memory leaks. And we see here all heaps are free, no leaks are possible, so everything is all good. So the CodeGrade setup will check for comments. It will link your implementation file to several mains and test out and check the output to make sure it all worked. And it will check for memory leaks as well. So you don't have to write any main, just implementation file. And again, to recap, you have to use this program, assignment 1, for assignment 3 when you have to implement various sorting algorithms. And again, for sorting, the hard part is you're going to have to do a lot of swapping in your array. So make sure the swap function is working. So anyway, that's sort of it in terms of this video. Hopefully the video did give you some insight for the assignment. So I guess happy coding, and until next time.